Okay. So what is remaining for us? In fact, it's I mean, now we are implementing multi-layer perceptron from sklearn. We will try also to implement. Can you see my screen? We will try to implement also. We will repeat it for MNIST dataset. I mean, I guess it was important, in fact, to try it, to let you try first using MNIST dataset. MNIST dataset, it's a dataset which consists of 70,000 examples, 60,000 for training and 10,000 for testing. And it's handwritten digits. You can Google it, for example, to get more information about MNIST. MNIST dataset, it's a very useful one, and it's very important in computer science because usually people use it for testing new algorithms, new tools, and stuff like this. And the digits have been normalized and centered in a fixed size image. Each image size is 28 times 28 pixels. So now we are working with images. I mean, so far we have been working with numbers, right? We have been working with iris dataset, and in iris dataset we have scalar values. We have some numbers. We have 4 features, and each feature has a number. Now we will work with pixels or images, and it's the same. In fact, images, it could be, I mean, one channel grayscale image, and the pixel value, it could be number between 0 and 255. So this is the case, in fact, in MNIST dataset. But now it's a good news for us because we are started to work with images instead of working with just numbers. So I just repeated the example. In fact, I mean, in this MNIST dataset, instead of having 4 classes, 4 features similar to such as the case of iris dataset, now we have the image, and the image is it's 200 times 200 pixels. So so each image, in fact, it's like a matrix, and this matrix, it consists of, I mean, a grid, for example, and each one here, it's a pixel, right? So it consists of some pixels like this one. This one, it's 28 times 28, right? Which is 780 watt. Can you try? Can you check it? How many features? So when it's 28 times 28, so it's 784. So imagine now we are moving from simple systems like an iris dataset to a more complex system. So the system now we have this number of features. So we have this number of features, the 784 pixels or features, for example, and each feature has a value. So each pixel, it's the value of each pixel, it's number between, in fact, 0 and 255, right? So if you want to normalize it, just divide it by 255. So the minimum value is 0, maximum value is 255. So do you remember the equation for normalizing? If you want to normalize each pixel, so it will be x minus x minimum divided by the range. The range, it's x max minus x minimum, which means it will be hx divided by 255, because the minimum value is 0, the maximum value is 255, so the range is 255. So in fact, if you want to normalize those images, so each pixel value will be a number between 0 and 1, you just need to divide it by 255, which is very important to normalize and standardize your dataset. We cannot accept those large values, because those large values, if we are using any kind of activation function, we will lose lots of information, and I described it last time. So imagine that we are using this Gaussian function, for example. So the Gaussian function looks like this one. So I mean, this number here, it's around 2.5, which means if we are using this one, in fact, as it is, we will lose lots of information. We will keep only small values. I guess when it's white, it's a 0, right? When it's black, it's 255. Is that correct? Yeah, 0 is black, in fact, and 255 is white. So 255, this is white. And 0, it's black. But we have also, it's a grayscale, in fact, so we have all numbers between 0 and 255. So now we need to display it. We need to play with it. So we will use also, I mean, in fact, MNIST dataset, it's located in many libraries. So this time I will take it from keras.datasets. So we can get MNIST from keras. MNIST, we will get it from keras.datasets. And so the dataset will consist, in fact, we will upload the dataset. So it's MNIST.load data, and it's already shuffled, divided. So it's just ready. So when you upload it, you will get the training part, the training set. We will get X-train, Y-train, and we will get X-test, Y-test from Keras. It's already ready-made in Keras, in fact. It's shuffled and it's fine. You just need to use it. And it's prepared in this way, 60,000 for training and 10,000 for testing. So when you're uploading it from Keras, it's already just, you just need to use it, right? So this is my data set. If you want to print the shape, you can get the shape. If you want to visualize it, you can just visualize some digits using image show. Why image show? Because it's image, right? And each image, in fact, it's 28 times 28. So each one, it's like this one. It's 28 pixel times 28 pixel. 0 means black. So when you have a pixel value, so 0 means black, until 255, which is pure white. And we have all the gray colors in the middle, in between. We need to prepare the data set for training. How can we prepare it for training? I mean, each image is 280 times 280. And if you remember, in neural network, we have the input layer. So the input layer, it will deal with those 28 times 28 pixels as one vector. Do you remember? So the input must be flattened. It must be like this one. So we need to convert it from this one into this one, from 28 times 28 image, right, into a vector. So this one will be, pixel 1, 2, 3 until 784. It will be like this one. How can we do it? Because in this way we can use this input vector for my neural network. I mean, in my neural network expecting all images to be in rows. So we need to convert this one into a row vector. So it must be like row. So it will be like this one. The data set will be a table. So this one will be the target feature, right? Image, maybe it's 0, 0, 0, 1, 1, 1, 2, 2, 2, and so on. So this one will be in pixels. So we will start with pixel number 1 until we go to pixel number 784. So it will be like this one. So each image should be represented as a row vector. How can we do it? Using this command here. Just reshape. We just need to reshape it. This one. I mean, the training data set, it's 60,000 images. So we need to reshape it in this format. So now we are converting it into a table. We need to convert it into this shape. So this table, in fact, it will be 60,000 times 784. So using reshape. So we just reshape it. We divide each x value by 255, right? So I'm dividing the train value by 255. X test, I divide it by 255 because I want to normalize it. So in this case, we normalize. If you don't want to normalize, just remove this one and test your results. You will see the difference in accuracy. Big difference, in fact, in the accuracy. So after that, I will import my MLB classifier. My MLB classifier we will import it from sklearn.neural network. So we will get it from here. So this is my MLB classifier. We will get MLB classifier. I just need to select the solver. I'm selecting here SGD. It's a stochastic gradient descent. I mean, if you can Google it, you will find lots of solvers. There are many solvers. So I will use SGD. SGD, it's a stochastic gradient descent, which is very suitable for online learning. I mean, in stochastic gradient descent, we train the model example by example. And when you train it example by example, it means in the future, if I got some new examples, I can just retrain the model using those examples one more time. I will use activation function, which is logistic regression, logistic function. This alpha and those numbers, I mean, this one, it's related to L2 regularization technique. We will use here 2 hidden layers. The first one consists of 100 units, and the second one consists of 30. Random state, maximum number of iterations, verbosity. This one, it's true. If you want to print out, I mean, the training process numbers from training, I mean, this is the learning rate initial value, and this is a total value. I mean, this total value is for termination criteria. If you want to stop training, I mean, when the model will stop training, when there is no change in the loss function, for I guess for 10 epoch, it will just terminate. It will stop when there is no improvement. So for this model now, if I want to plot it, I will try to plot it simply. So I will have some inputs. So the inputs will be my image, my pixel values, right? We will draw it like this one. So this is pixel value number 1, 2, 3. This one will be 784. In the first hidden layer, it has 100 units. So it will be like 1, 2, until 100. 1, 2, until 100. All those are connected here, right? We have all those connections. So this is the first hidden layer. The second hidden layer, it consists of 30 units. So we will have here, it will be smaller. So it will be like from 1 to 30. All those weights are connected, right? So it will be like this one. And finally, we will have an output layer. What will be the size of the output layer? The size of the output layer will be the number of classes. How many classes in this MNIST problem? In this MNIST dataset, we have 10 classes because we try to classify into 10 digits. So 0, 1, 2, until 9. So we have 10. So we will have here from 0, 1 until 9. And all those connections are connected. Right? So it will be like this one. So the neural network.
I have a question, Ibrahim.
Yes.
The learning rate, is this dynamic in this class or this MLP classifier?
What? One more time, please.
The learning rate.
Mm-hmm.
Since you're just setting learning rate in it, does that mean that the learning rate is dynamic in this?
I guess yes. Yes, I guess it's a dynamic. So starting with this value, and but you need to check. You need to check the documentation of sklearn, in fact. So I have it here, so I can go back to it. So learning rate, it could be constant value and it could be adaptive value. Adaptive keeps the learning rate constant to learning rate initial as long as training loss keeps decreasing. Each time two consecutive epochs fail to decrease training loss by this tool will fail to increase validation score. So each time the learning rate will be divided by 5. So when there is no improvement, so we start with this initial value because the learning will be dynamic. We will start with this value, and each time there are two consecutive epochs without improvement in the loss value, they divide the learning rate by 5. So we start from big value and it decreases to small value, in fact. So it could be constant, it could be gradually decrease the learning rate at each time step using an inverse scaling exponent of power t. So the effective learning rate will be the initial value divided by t to the power of t. And adaptive. So when we select this initial value, we will go for adaptive in fact. And it's only used with SGD. So this is the neural network, how it will look like. We will have input layer, we will have 2 hidden layers, and we will have 1 output layer. From this configuration, it's up to you to select numbers. We selected the first hidden layer consists of 100 units, and the second hidden layer, it has 30. And of course, the output layer will be 10 perceptrons. So if you need to calculate number of parameters here, can you try to help me? So the first hidden layer, how many weights in this layer? It will be 100 times 781 plus 100 bias value. So it will be this number. So this number will be the number of weights in the first hidden layer. The second hidden layer, we selected 30. So it will be 30 times 100 plus 30. Do you understand why this number? So the weight value for the, from the input layer to the first hidden layer, we have 781 inputs connected to those 100 units with weights. So how many weights? It will be a matrix. The size of the matrix will be 781 times 100. So it will be this number plus 100 bias value. So this one will be the total number of trainable weights in the first layer. In the second layer, it will be 30 times 100 plus 30. In the output layer, it will be 10 times 30 plus 10. So can you calculate the number?
81,840.
81,000?
840.
840. So it's a simple problem, in fact. So now we are working with a simple problem and a very simple structure, but do you see how many parameters? So it's 81,000. 81,000, it's a big number, and we need big data, in fact, to train this number. But we have huge data. I mean, this data set, it's 70,000 data points, right? So, but I mean, the idea here, when the number increases, when the neural network becomes more complex, it will be able to solve the more complex problems. Because in this problem, we have 10 classes. We are working with images, so it's not easy problem, and we need to really have a model which can be used for solving it. So now we will train the model.
I have another question, Ibrahim.
Yes.
Do we have to worry about the ratio between the dataset size and the amount of parameters?
Yes, I guess, but there is no any scientific recommendation for doing it. But okay. It's just imagine. I mean, if you have a very huge neural network and you have very small data set, it will be impossible, in fact, to it's like we will give you an exam in math, for example, at university level, and you just studied math for first and second year in elementary school, right? Is it enough? You just studied a small book like this in elementary school, for example, in first year and second year, and you need to take an exam now at university level in integrations and differentiation and really those complex stuff. Will you be able to really solve it with this small amount of data? So when the data is small, it would be impossible really to train all those models. You will have a model not trained enough, maybe, so it will have this underfitting problem. It cannot fit your data set. It will not be able, in fact. But of course, when the data set is small, we can use cross-validation, right? So because, I mean, this data set, for example, we need to divide it into one part for training, one part for testing. So in fact, we are holding out 10,000 data points for testing. Those 10,000 just for testing, we are not using it at all, just for testing. So if the remaining amount is not enough, we can just use the total amount for training the model, and we can use cross-validation for testing the performance of the model. So those 70,000, we can divide them into k folds, for example. Maybe you can select k equal 5, and we will use cross-validation to check the performance of the model. And after that, I will use the whole data set for training the model. We are facing this problem in real life, in fact, because some people, we had a PhD student who was collecting data from water facility in Öresund, and I mean, collecting those data is very expensive. It costs a lot, in fact, costs lots of money. And he has very few, in fact, he has maybe a very small number of data points. And in this case, we cannot sacrifice one part as a testing. So we use the cross-validation, and we try to simplify the model as much as possible. I mean, you need to start with a base model, for example, and after that, you try to just make it simple as much as possible. because you need to get a system which is robust and can generalize. If you just go for a very large model, it will be impossible to train this model using those few numbers of data. It will end up by maybe memorizing those data points. So if this model is really very complex, it will quickly, in fact, memorize, and it will have overfitting problem. So if you want to test it again, it will give you just, nonsense values, because we didn't have enough data to train it. I mean, it's capable, it has high capacity, in fact, and it memorized the data instead of training it. So we need to be careful about the amount of data, and we need to, but there are, in machine learning, in fact, there are many ways for increasing, the size of your data set. So, so there are methods, for example, especially in image, when you are working with images, you can add some noise to the image, you can rotate some image, you can do some transformations, for example, to double the size or triple size the data set which you have. Yes. So, for example, if you are collecting data for some people for face recognition, you can just ask them to wear hat, to wear glasses, remove it, take images in different light conditions, try to use some tools from image processing to transform it and to add some tricks, add some objects in the image and stuff like this. So you can just maximize the size of your data set. We had this problem last year. We had a group of students who has been working in image fish classification, as they didn't have a chance, in fact, to collect the data because of Corona situation. So they just decided to collect images by taking images of fish and make some marks in the fish and take new images, take images from different angles, and so on. So they try to maximize the number of images which they have. So now we will train the model. We can print also the score. Training score and testing score, for example. We can use it for predicting for the X test to get Y predict. And after that, we can generate our confusion matrix. So we can plot the confusion matrix. We can see it here. So we have the confusion matrix for the training and for the testing. And if you can see here, this is the diagonal. Now we are doing the confusion matrix for 10 classes. So we have, in fact, it's 0, this one 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 digits. From 0 to 9, we have 10 digits. So now we are plotting the confusion matrix for 10 digits. We try to maximize numbers across this diagonal. Other numbers here, it means the model is confused. So for example, what does it mean, this one? Right? So this one, in fact, it's a 0, but it was misclassified as 2. This one, for example, it's a 0, but it was misclassified as 6. And it's correct, in fact, at 8 as well, because 8, 9, some people, they write 9 like 0, 8 like even sometimes 3. So those, for example, this one, what does it mean, this one? This number, it's 8, but it was misclassified as 4, right? 8 misclassified as 4. We have this one, for example, so it's 20 cases, 20 images, which is 6, and it was misclassified as 0, right? So the accuracy at the end, we can get the accuracy. The accuracy will be 99 in the training and the 94% in the testing. Of course, you can tune the model and you can adjust parameters. You can try to select, you can increase the number of iterations, for example, to get much better results. 94%, it's not good, because in this model, we should be able to reach maybe 98%. So it should be something like this one. But we started with a simple model, and this simple model, we just trained it for 100 iterations. Maybe if you will put this one equal 1,000 or 10,000, you can achieve much better results. Yes, and you have the code MNIST MLP. So you can go for GitHub, run MNIST MLP. I guess, some questions from you. I don't know where is this chat. Please let me know if you have any questions, because I cannot open the chat room. I can see just some people are writing, but I cannot see it, in fact. Yes. So you can go. I mean, I can go with the next example also. If you want to take 5 minutes to go to this code, please, in GitHub, and try to run it. Try to change. Try to increase the number of hidden layers. I mean, we have hyperparameters. I mean, we have two types of. I can't see it now. Yes. Yes. Yes, correct. 784. I guess. Yes. So in fact, in this model, you can go back to the model. You can run it in. You can run it, but using different hyperparameters. All those we call it hyperparameters. So the solver, it's a hyperparameter. The activation function, it's a hyperparameter, right? The number of hidden layers and the number of units in each hidden layer. This one, it's hyperparameter. The learning rate, it's a hyperparameter, right? All those are hyperparameters. Those hyperparameters, you can change it by yourself. Or maybe you can use search grid, for example, to try different combinations of those parameters. If you want to, I mean, if you want to automate this one. So you can select now by random, by trial and error, but also maybe you can say, okay, I will test 2 hidden layers, 3 hidden layers, 4 hidden layers. And with 100, 150, 120. So you can use search grid for doing it. So the computer will just run it for all different combinations, and it will give you the best model at the end. Here we didn't use cross validation, so maybe if you use the cross validation, maybe you will get better results. So just go to this GitHub file and try to change those parameters and try to run it one more time to get some different results. Yes. I mean, the next slide, in fact, it will be the same, but we will use Keras. So instead of using MLP from multi-layer perceptron from sklearn, we will use it from Keras. Keras is very important, especially for people who will work in deep learning. Maybe in your project next semester, you will be working with deep learning. No one knows, right? So now in this course, you are just studying shallow learning, but maybe next semester you will have the background, in fact, which will help you to just go for deep learning. You can go for deep learning as a black box, in fact. So you can just use the tools as a black box, and with time you will get the knowledge behind it, how it works, and what is the difference between different types of models. But Keras is a very important tool. It's a very important package for people who want to work with machine learning. So we have sklearn, for example. This is very good. It's a great tool. We have Keras, we have PyTorch. So PyTorch, it's a new, most advanced. So do you need some time, or should we go to the next slide so we can finish that? We have 3 slides here. It's just this example using Keras. We need to build this model from Keras. So we can take, we can finish at 12:30, for example, and we can take some longer break. So we can go for more examples and try it. So it will be the same here in Keras. We will import the dataset from keras.dataset. We did that last time, right? If you want to import it from any source, it's up to you, no problem. In Keras, in fact, if we need to build a model, we need to do it in 2 steps or in 3 steps. We need to import a sequential model. So from keras.models, we need to import a sequential, because the model will be a sequential or a sequence of layers. And we need to import layers. And we need to build the system or the model. We need to decide how many layers we need to add to our system, and we will just add it to the sequential model. So first we will import sequential from keras.model, and after that we will import dense layers. In Keras, this layer, they call it dense layer. This one, they call it dense layer. So this one, it's layer. So we will build a model, or we will import a model. We will call it a sequential. So first we have our data set here. We will get the model equals sequential. And after that, we will add some layers. I mean, the model which we used last time, it has 3 layers. Do you remember? This model has 3 layers. 2 dense layers, you can just call it 2 dense layer and 1 output layer, or 3 dense layer. So in Keras, they call it dense layer. So this one, it's dense layer, dense layer, dense layer. I mean, in feed-forward neural network, we call it hidden layer 1, hidden layer 2, and the output layer. But in Keras, they call it dense layer. So here I will import a model and we will add some layers to it. We will add 3 layers, similar to the other model, right? So the first layer, it will have 350 units. The second layer will have 50 units. And the third layer will have number of classes, which is 10, in fact. So you can just remove number of classes and you can just say it's 10. Here, in fact, in Keras, we have more control, more better control. So the first hidden layer, for example, it has some input. So the input will be 28 times 28. We know because the image anyway, it's 28 times 28, right? So we need to flatten it, correct? It need to be flat. It need to be a row vector. So we will reshape it into 28 times 28, right? And the activation function, what activation function you want to use? Here we are using ReLU, rectified linear unit. And how many units, how many neurons in this layer? It will be 350. We will add another layer. So just model.add, first dense layer. The second dense layer, it will be 50 units. The activation layer will be ReLU. The third one, which is the output layer, it will consist of 10 units, right? 10 units, and the activation layer will be softmax. Softmax, because this softmax, it will give us this cross entropy. It will give us normalized probability, in fact. So we have 10 classes, for example. So we will have here some 10 classes. So if you have an image and this image, it's maybe it's 5. So maybe we will get the probability for 0 to be something close to 0. This one will be 0. And when it's 5, it will be maybe 0.9. This one, maybe it will be something 0.01 something. So in this case, we will understand that this one, it is a class which we are looking for, right? So the first layer, it will has activation function ReLU. ReLU, it's very good for vanishing gradient. In fact, it's a very smart one. And in this case, in fact, we don't need to normalize. So if you will use ReLU, you don't need to normalize. If you want, remember, ReLU, it looks like this one. Do you remember this one? So in fact, all x values, which is positive, it will be mapped into just x. And the equation for it, it was max, 0, and x. So all negative values will be converted into 0, and all positive values will remain as it is. So if you will use ReLU here, in fact, you don't need to normalize. And in deep learning, we don't normalize. We don't do anything. We just use raw data. So when you are working with deep learning, you don't need to do anything. Just work with raw data, right? So we don't need to care about data normalization, standardization, and so on. So if you will select this ReLU here, in fact, you don't need to normalize. So we will see if I normalized or not. So we will. So we have 3 layers. We have 3 layers here, 3 dense layers. We will add them to the sequential. The sequential, it's a platform, for example, for our model. And after that, we will compile the model. And when we compile the model, we need to decide the loss function. We will use a categorical cross entropy loss function. We will select the optimizer, and we will select what kind of metrics we need to display the output accuracy. We need to see the accuracy. And after that, we will fit the model using X-train, Y-train, right? X-train, Y-train. Number of epochs, it's 100. We will use batch learning, batch gradient descent. So in this case, we will select the batch size 512. I mean, this number, it's hyperparameter. You can select this one. It's according to the hardware which you has, for example. So if you have a GPU and the GPU has a low GPU memory, for example, which cannot afford this batch size. So in this case, you can just decrease it a little bit and so on. This is the verbosity, how much you want to get output from, I mean, printing out from the algorithm. This is the validation split. I mean, from this training data set, we can take part for validation, right? So in this case, we selected 20%. So in fact, we can use 20% from the training data set for tuning the model hyperparameters. Test results, it will be model evaluate using X test, Y test, and so on. So we can just do it and we will see. You have also the code, it's called MNIST Keras. And after testing it, we should get better results. And this is what I have been expecting. Use cross entropy, we can reach 98.2%. So we have here 92.8%. And also you can tune it a little bit to maybe reach 99% or 99.9%. This problem, it's not a very complex problem. and you should be able to reach maybe 99.9%. It's like election, I mean, results of presidential election in my country, in Egypt. I mean, all presidents, they got this score at 99.9% all time. So they are just perfect. So we have also something very nice advantage here in Keras. In fact, you can also write model summary, and in this model summary, it will give you this table. When you are using model.summary, it will give you, I mean, details about your model. Your model, it's a sequential model. It has a number of layers, 3 layers. By the way, you can decide here. You can also specify the name of each layer. So you can just call this one. It's first hidden layer, second hidden layer, output layer. I didn't give it a name, so the system automatically will give it some names like dense _1, dense _2. This is the output shape, right? So the output here will be 350 values, 50 values, 10 values. The input, it will be here 28 times 28, correct? This is the number of trainable parameters. So this is the number of the first dense, right? How can we get this number? In fact, it will be 350 times 784 plus 350, correct? Because we have in the first layer here, we have 350 units times number of inputs, which is 784 plus 350 bias, correct? What about the second one here? The second one here, it will be 50 times 350 plus 50, correct? Because in the second layer, in the second dense layer, we have 50 units. So the number of weights or connections between the second layer and the first layer, it will be 50. This one times, in fact, 50 times 350 plus 50 bias. The output layer, for example, the output layer, it's easy. It will be 10 times 50 plus 10. So it will be 510. So now we can understand. I mean, when you are using Keras, I guess if you will be using Keras, you will not go to sklearn, because you have here good control about all things, and it's just easy. It's like building blocks, in fact. So it looks more easy and more easy to control here. From Keras utility, we will use two categorical. This one, we will use it because, in fact, in Y, I mean, the labels here are given like in this way. It's just 0, 1, 2, 3, 4, 9. It's like 10 labels. So we need to convert it into one hot encoding using two categorical. When we use two categorical, in fact, we are doing a one hot encoding. One hot encoding means, so for example, the label of the first image, for example, it's 0. I cannot use 0 like this one, but I need to convert it into one hot encoding. So it will be, if the labels is 0, 1, 2, 3, until 9, for example, so it will be 1 when it's 0, and zeros otherwise. So we will use this one. So we have categorical, and also you can get a reverse of categorical, right? So if you have it like this one, also we should be able to get it back into a categorical or a label. Yes. So I mean, the last part here, in fact, after training your model, because when you are training a model, for example, in your bachelor project, for example, you will be collecting data. Maybe if you are working with a company, for example, classifying fish, for example, you will collect a data set. Maybe you will have a GPU. You will train your model for weeks. It could happen. In fact, you can have a large data set. You have a very good model, and you will train your model for a number of weeks. After those number of weeks, you need to store your model, right? So you need to save the trained model. We need to save the trained model, because I don't need to train my model one more time. So once you build a model, you spend lots of time for training it. Now I just need to save it in a file and just upload it when I need to use it. I don't need to start this process from scratch each time, because it's time consuming, right? So once you build your model, you will train your model, and you need to save your model in a file, so you can just upload it anytime and just use it. And if you will implement your model in a hardware, for example, I just need my weights. So imagine that I trained a perceptron, right? I trained a perceptron, and once we trained it, now we know the values of omega 1, omega 2, omega 3, and the B. So in fact, my model, it should be only those values, omega 1, omega 2, omega 3, and B. I need to store those values because those values are money, in fact. So in fact, if you are building, imagine you are building a model for classifying fish for a company, and you collected data, and it cost you money to collect the data. You bought GPU for training your models, and finally your model will be those numbers, those set of weights and bias value. Those numbers are money, in fact, because if you will give it to the company, maybe the company will use it in their production lines. They will save money. They will improve the quality of production, correct? So they will make money from those weight values. So those weight values are money. You need to store it in somehow, in a file, for example. And if you need to give license to companies to use those weight values or model, for example, you need to protect it, for example, and so on, because those values are expensive, because you spend the time, you spend the effort, you collected data from different sources. I mean, you bought computers and GPUs for training your model. So this is your product at the end. So we need to store those numbers in a file and upload it when we want to use it. So we don't need to train our model each time, because if you want to train your model each time, you need to move with the data sets which you has been collecting. Maybe those data sets, it's impossible to carry, right? Imagine you are building a model for patients' diagnosis of kind of a disease, and you have lots of patient information in your computer. You cannot move those information from your computer to home and to somewhere else. It's impossible, right? But I can move my model. My model will know nothing about my patient. I use the information in the data set for training the model and for adjusting those weight values. But once I build my model, I am free to use my model anywhere. I can import it, export it to some companies to use it, but I cannot give them access to the data, right? So we can use the model, but we cannot use the data itself. And this is I mean, those a problem about privacy and stuff like this in machine learning. So in fact, once we train the model, we don't need the data. You can just give the data back to the people. Clean your computer. I don't need the data really. And try to be honest. I don't need to keep your data with me because I trained my model. My model now, we can make decisions. If I got new data set in the future, I will retrain my model, but I will not start from scratch. You will not start from random values, right? You will start from those values, and we call it, I mean, in Keras, I guess in scale-learners, they call it warm start. So warm start means we are not starting from zeros, initial or random initial weights. We are starting from some values, from trained values. So when you start from this one, so if you will use SGD, for example, and you got some new data in the future, so in this case, you don't need to start from scratch. You can just start from those weights and try to modify it to absorb the new knowledge which you got from the new data which you just received. You don't need to start from random values. So when you are working in your code now, you need to learn how to save all those trained models into files and store it and import it later on. This is very good skill and very, very important, because when you train your model for a company or whatever, you need to know how to help them to apply it in real life and to save it in a safe place and stuff like this. Because I mean, if we will train the model each time I got a patient or something, it's impossible. It will be impractical, in fact. Yes. So we finished this slide. It's from last week. So I want to give you some time now to work with, work with those two examples, those from Keras and from sklearn, and we can meet after. Maybe we can meet at 1, for example. What do you think?